Hey there, physics fans. Today we're going to work text problem 10-92, and I'm going to utilize this flipped classroom tools on the iPad to help you see my notes a little clearer. So first up, I'm going to go through this read step. And you'll notice that I'm dealing with a pulley with a moment of inertia. So a moment of inertia indicates that pulley is going to have mass. And then I'm also going to read through the rest of the problem. It says that there are two circumferences of the pulley and that light strings are wrapped around them and that there are weights attached. So the light strings indicates that the rope is massless. And then this two circumferences of the pulley, that means that if I have to use Newton's second law, I'm going to draw a little bit of a different free body diagram. And then the problem asks two questions. It asks for the angular acceleration of the pulley and it asks for the linear acceleration of the weights. And it provides us quite a bit of data. So I go into tasks, and that's where I'm going to start out with, where I say for part A, I need to write this angular acceleration, which is our alpha symbol. And then for part B, I need to utilize the symbol for linear acceleration, which is A sub t, or translational acceleration. But I'm going to have to do it for both mass 1 and mass 2. And that's because their distances from the axes of rotation are different. So they'll have the same angular acceleration, but they're going to have different linear acceleration. And then I go into physics. Well, the problem does not give us any information as far as a definitive start or stop point for the masses. So we can't use kinematics, we can't use conservation of energy. There's no collision here, so we're not going to use any sort of conservation of momentum. So we're left with Newton's second law. But that's how we're going to have to approach to solve these variables. And because there's both translational motion and also rotational motion, I'm going to have to use both of our Newton's second law equations as written on the PRC. So sum of all external forces equals mass times acceleration, and then the sum of all external torque equals the rotational inertia, or object's rotational inertia times its angular acceleration. And then a couple other equations I think will be helpful is going to be this angular acceleration times r is equal to the translational acceleration. So that link equation that's on our PRC. That brings us to the draw step. We have a really good drawing here. I'm just going to highlight the fact that the radii of the circles are different and highlight them a different color. And then that brings us to givens. So the textbook, notice I put little dots here. The problem is not given it to us. So without those dots, that means that it's 1 sig fig. With dots, if the book had printed dots there, then it would be 2 sig figs. So I'm going to go with my 1 sig fig for these two r's. So r1 is equal to, and I'm converting it to meters, 0.5 meters, and then r2 is equal to 0.2 meters. Mass 1 is equal to 1.0 kilograms. So that's nice. We don't have to do that conversion. Then we're also given the mass 2. The other thing we're provided is that rotational inertia of the pulley, which is 2.0 kilograms meters squared. So that's nice. We don't have to actually solve for the mass of the pulley. We're given it the rotational inertia, so it's one less step we'll have to do. Next up is our assumptions. So we're already told that the rope is massless and frictionless. It doesn't tell us that it's frictionless, but I'm going to assume rope is frictionless. We already know it's massless. And then I'm also going to assume that the pulley is frictionless. There's nothing in the problem provided to us for it to be friction, to have friction. So I'm going to assume that there's no friction. We're ready to solve, but we'll do that in the next video.